from the first-person perspective of Alonzo Church. I'm not much of a party-goer, never was. But that evening, I made an exception to join the gathering at John von Neumann's elegant home. It was not so much the promise of free drink or good food that tempted me, although both turned out to be excellent, but the knowledge that Alan Turing and Kurt Gödel would also attend. The three of us had, quite without intending to, hammered the final nails into the coffin of David Hilbert's dream. And ironically, we had done so by showing exactly how to formalize mechanical computation. In my mind, it all started as a technical problem. We needed a clear definition of what it means for a function on the natural numbers to be effectively calculable. So I introduced the lambda calculus, a formal system that captures the idea of defining and applying functions in a purely symbolic way. This served as my foundation for understanding what a mechanical procedure could be. I still remember the hush at the mathematics department at Princeton when my results and Turing's, using his Turing machines, converged to the same concept, the set of functions that are computable by a mechanical method. But I am getting ahead of myself. Let me start with that evening in the spring. I arrived at the party, pipe in hand, though I knew better than to light it in von Neumann's well-appointed interior. John greeted me with his usual exuberance. He really did know how to make one feel welcome. I was sure I'd be left to mingle, but I was relieved to see a few friendly faces from the mathematics department, people more at home discussing the finer points of symbolic logic than dancing or gossiping about local affairs. I recall drifting through the main hall. There were paintings on the walls, landscapes, if memory serves, soft lighting, a faint smell of cologne and perfume from the other guests. I found the brandy, poured myself a modest glass, then tried to keep to one side of the room. Social gatherings can be overwhelming. But John's house was large enough that I could find a quiet nook or two. I spotted Turing from across the room. He, too, looked a bit out of place, hands in his pockets as if uncertain what to do with them. We nodded to each other. I thought about going over, but before I could, Kurt Gödel stepped in from the foyer. Gödel looked about as comfortable as I felt, which is to say, not very. I decided to greet him. We chatted amiably for a few minutes about the Institute, about mutual acquaintances, about the weather, anything but the big subject we all knew we'd eventually discuss. The Library Interlude. Eventually, John corralled us, Turing, Gödel, and me, toward a side room and then into his private library. I always liked John's library. His collection was eclectic, with volumes on mathematics, physics, even some whimsical detective novels. My eyes roamed over the spines, but soon John was pouring us drinks and inviting us to sit. It was an intimate, comfortable room, dark wood, a warm lamp, and that sense of hush. He began by stating our purpose to reflect on the end of Hilbert's program. My immediate reaction was a subtle ache of nostalgia. I never personally pinned my hopes on Hilbert's program as firmly as some others did, but it was still an inspiring notion. Unify mathematics, show it's consistent, and devise an algorithmic process to decide any statement in it. A grand vision indeed. Yet, here we sat, the authors of works that systematically dismantled that dream. In 1931, Gödel had proved that any sufficiently strong axiomatic system could not be both consistent and complete. By the mid-1930s, Turing and I had proven there was no general decision procedure for all mathematical statements, the Entscheidungsproblem, a negative resolution, the final blow. I listened as John introduced the topic, then I offered a few words about lambda calculus. I suppose we've discovered a silver lining in the negative result, because in order to prove the decision problem was unsolvable, we had to define precisely what a mechanical procedure is. My approach used the lambda calculus. Turing's used a machine-based model. Remarkably, both definitions coincide. Turing chimed in. Yes, it's a stroke of genius on your part, Alonzo. I found your system quite elegant, though my own mind leans more to the mechanical perspective, imagining an actual machine scanning symbols on a tape. I waved a hand. Don't discount your own insight, Alan. I read your paper. It's a brilliant demonstration of how any function that can be calculated by a human mathematician following a finite procedure can equally be computed by this so-called Turing machine. I paused for a moment to catch Turing's eyes. In fact, I think your approach is more intuitive to the layman, though the lambda calculus is perhaps more convenient for deeper theoretical expansions. Gödel, seated quietly, made a small sound of agreement. It's fascinating how these definitions converge, and they also align with my own recursive function approach. Indeed, it seems there is a single concept of computability that arises no matter how one tries to formalize it. John nodded enthusiastically. Yes, precisely. And that is the heart of Church's thesis. Here I interjected. More of a hypothesis, or an identification, if you will. The Church-Turing thesis states that our definitions of computability capture all processes that can be computed by any effectively realizable method. John raised his glass. However we name it, it's a momentous result. We discovered that Hilbert's hope for a universal decision procedure fails because we can precisely define what it means to compute and then show certain things are not computable. Alan wore a thoughtful expression. You know, if we had to sabotage Hilbert's program, at least we did so with something constructive, a new field of computability theory, and ironically, we might yet see wondrous machines built upon these negative results. I recall that struck me deeply. Yes, it's a curious inversion. By proving we can't mechanize all of mathematics, we ended up giving instructions on how to mechanize certain things. We've unleashed a new domain, the art and science of constructing mechanical solvers for those tasks that are, in fact, solvable. The universal machine concept, for instance, is quite powerful. Gödel, swirling his drink, added softly, I always wonder about the philosophical consequences. My own theorems show that mathematics is inexhaustible. There's always more statements out there that can't be pinned down by any single axiomatic system. Turing's result, yours, Alonzo, show that there's no single mechanical method to settle all statements. I wonder if this says something about the human intellect or the nature of reality itself. We fell silent for a moment, letting the weight of the ideas settle. Then John changed the mood slightly by hinting at the future. If any of you have spent time thinking about how these universal machines might be implemented in electronic form, you'll see we're on the cusp of a revolution. I perked up. That seems so futuristic. Our logic is mostly pencil and paper mathematics. Are we truly so close to building machines that can carry out any symbolic manipulation at high speed? Vacuum tubes, circuits, these are new technologies, but do they have the reliability to handle large-scale computations? Well, Turing answered, they might, in time. The problem is partly one of engineering, but the concept is there in the mathematics. Once we harness stable electronics, we could realize a universal Turing machine physically. Imagine punching instructions onto tape, feeding it to a machine that reconfigures itself as needed to solve different problems. John nodded vigorously. I'm telling you, if we can solve the memory and reliability issues, we can do extraordinary computations. Weather predictions, cryptography, nuclear physics calculations. Think of the potential. And from what we've discovered, the only boundaries to these machines will be the limitations we've mathematically proven. Not everything is decidable, but an enormous amount of mathematics remains within reach. Gödel, eyes shimmering, said, That's the beautiful paradox. We can build a universal machine, and yet we know from our own theorems that not everything is solvable. The machine is universal in terms of what it can compute, but there are some questions it cannot settle in principle. Fascinating. I took a sip of brandy. We might one day see attempts to replicate not just arithmetic, but reason itself, in a machine, perhaps even something akin to intelligence. But the question remains, does that machine remain bound by the incompleteness theorems, or might it step beyond them as a living mind can sometimes do? Alan gave a slight shrug. I suspect even living minds are bound by these theorems, but that is perhaps a question for philosophers. For now, we can say that Hilbert's purely mechanical dream for mathematics has been proven unattainable. Maybe that's for the best. And so our conversation meandered, merging the technical with the philosophical. I found it invigorating, yet also humbling. I had never sought to bring down Hilbert's program. I admired Hilbert greatly. My research was simply a quest to clarify the foundations of logic and computation. The negative result was but a byproduct of that quest. Yet here we were, reaping the consequences and glimpsing the possibilities that could arise from these new understandings. Resuming the party. Afterward, we rejoined the larger gathering. I drifted back into the main hall, noticing how the party had grown louder as the hours passed. Glasses of wine were clinking, laughter echoed around corners, and small clusters of students hung on every word from a professor or two, eager for some nugget of insight. I found myself cornered by a group of younger mathematicians. They started asking about the lambda calculus, what it was, how it worked. One or two had read my papers. Others were simply curious because they had heard about this Church's thesis. I tried to explain, in simpler terms, that the lambda calculus is a formal language for defining functions, variables, abstractions, applications. These are the building blocks of the system. One can encode numbers, booleans, recursion, and all manner of computational processes. My hope was to show them that something seemingly abstract could unify the notion of an effective procedure. One student asked, "So does this mean you can't solve mathematics with a machine?" I considered how best to respond. It means you can't solve all mathematics automatically. There's no universal program that says, "Give me any statement, and I'll tell you if it's true or false." But for certain kinds of statements, yes, we can write a procedure. It's just that Hilbert's grand desire for completeness is beyond our reach. Another asked, "What do you think this means for the future of mathematics? Is it a dead end?" I smiled. Not at all. We have discovered fundamental limits, but that only means we'll search for new methods and new forms of insight. Also, we might build mechanical devices to handle computations that are too large or tedious for humans. Those devices won't solve everything, but they'll help with many practical tasks. The students seemed both awed and a bit disappointed, awed by the depth of the discoveries, disappointed that there wasn't a neat resolution. I tried to reassure them that mathematics thrives on open problems and that the incompleteness and undecidability results make the field more vibrant, not less. An unexpected conversation. Later that night, I found myself in a quiet corner, sitting on a small sofa. I was a bit exhausted from all the talking. I noticed Kurt Gödel standing nearby, seemingly lost in his own world. I motioned for him to join me. He sat, and for a moment we listened to the distant chatter. Then I asked something that had been on my mind. "Kurt, do you think the incompleteness theorem suggests that human mathematicians have some non-mechanical insight, or do you think it's all still mechanical at the end of the day?" He took a moment. "I've struggled with that question. My personal belief leans toward the idea that the human mind surpasses any fixed formal system, but I can't prove that. Philosophically, I suspect there's more to intellect than mere computation. Yet the mathematics of Turing machines and the lambda calculus is quite compelling. Perhaps the question can't be answered with the tools we have now." I nodded. I, too, wonder if there's something intangible about creativity, about how mathematicians jump to new axioms or form intuitions that outstrip the current system. In a purely mechanical approach, you'd have to systematically search all possibilities, but humans make leaps. He shrugged gently. Leaps, or leaps of faith. In any case, the theorems show that no single set of axioms can capture all mathematical truths, so the capacity to choose new axioms might be beyond a purely mechanical method. Then again, maybe there's a mechanical method that systematically tries all consistent extensions of a system, so eventually it enumerates any given truth. That is possible in principle, though not necessarily in practice within finite time. It's a puzzle. We shared a melancholic laugh. "The puzzle of human thought," I said. "Perhaps that question will motivate future generations. For now, we at least understand the line that Hilbert's dream cannot cross." Gödel and I parted ways soon after that. I recall feeling a sense of reverence for how our separate journeys had converged on a single theme: the inherent limitations of formal systems, and by extension, the subtle interplay between what can be computed and what cannot. I had gone down one path, lambda calculus. Turing had chosen another, his machines. Gödel had approached from a higher vantage point of metamathematics, but all roads led to a final revelation about the boundaries of logic. Final thoughts that evening. I left the party sometime around midnight, stepping outside into the crisp spring air. The lights in von Neumann's home glowed warmly, and I saw silhouettes of guests still moving inside, finishing the remains of the buffet or the drinks. I placed my pipe between my teeth, finally lighting it once I was out in the open. As I walked home, I felt a mixture of satisfaction and longing. Satisfaction because we had achieved a monumental clarification of the nature of mathematics. Longing because a part of me wished I could rewrite the laws of logic so that Hilbert's dream was true, so that mathematics was a shining, complete edifice. But that was not to be. Reality, or at least logical necessity, had spoken otherwise. I found some solace in the knowledge that the negative result was also a generative one. We had carved out the domain of computability and begun the journey toward machines that might transform human life. The next few decades would see these ideas blossom, though none of us could quite predict the details. Perhaps Hilbert's defeat would pave the way for a new era in which we harness logic in extraordinary ways, from cryptography to artificial intelligence. With such thoughts drifting through my mind, I made my way through quiet streets, lamplit and serene. Princeton at night can feel like a place untouched by time. Yet I knew that even in that stillness, we had already forever changed the course of mathematics, logic, and the future of computation. Episode 3. From the first-person perspective of Alan Turing. I can scarcely recall any event that filled me with such mixture of enthusiasm and trepidation as John von Neumann's party that evening. Truth be told, I'm not the most sociable individual. Never have been comfortable in crowds. However, the chance to talk intimately with von Neumann, Alonzo Church, and Kurt Gödel about the ramifications of our work was too tempting to pass up. I arrived earlier than expected, around 7 o'clock, which left me in an awkward situation of standing in von Neumann's foyer, feeling like some stray cat that wandered into a palace. John, ever the gracious host, immediately put me at ease. He teased me gently about my punctuality, led me to where the drinks were, and told me to make myself comfortable. It wasn't long before Alonzo Church appeared, pipe in hand, quiet and poised, and then Kurt Gödel arrived with that distant look in his eyes. My mind was abuzz. So many questions, so many ideas. But I held them in check until John signaled that we should retreat to his library. An unusual confession. While we were in the main room, waiting for a chance to slip away, I recall being buttonholed by some earnest mathematician, I don't recall his name, who kept asking me about my machines. He seemed genuinely perplexed at how something so simple in description, an infinite tape, a read-write head, and a set of rules, could capture the entirety of mechanical computation. I tried to explain. Well, the tape can be of arbitrary length, which is crucial. The instructions, or table of behavior, is finite in length, but the machine can shift to different states and read or write symbols to the tape, thus encoding arbitrarily large computations step by step. It's not so much the complexity of the machine as the unboundedness of the tape that does the trick. He nodded, though I suspect he found it all quite abstract. I ventured, "You see, the point of a Turing machine is that it's not specialized. With the right encoding of instructions, it can emulate any other Turing machine. That's why we call it universal." He blinked and asked if I might offer a demonstration. I laughed politely. "It's more of a theoretical construct at the moment," I said. "We haven't built an actual universal machine, but theoretically it's all there. One day, perhaps, we'll see mechanical or electronic versions." Eventually, John freed me from that conversation by ushering me and the others into the library. The discussion in the library. Seated in von Neumann's library, I felt an electric excitement. I'd conversed with Alonzo many times at Princeton, even taken courses from him. But I had not had as much opportunity to speak at length with Kurt Gödel or to hear John's unfiltered thoughts about the future. John started by addressing us. Gentlemen, we are living in a time when Hilbert's dream has all but collapsed, and I believe it's largely due to you three. I had a small hand in encouraging some of that research, but really, the impetus is yours. So, let's talk about that. Let's talk about the ramifications of this collapse. I remember feeling a slight churn in my stomach. Did I break mathematics? I responded with a small grin. I never set out to bring down Hilbert's program. I simply wanted to clarify what it means to compute something. The negative result came as a sort of corollary. Once we define computation precisely, we can show there's no mechanical solution to all of mathematics. Alonzo nodded and added something about how his lambda calculus was intended as a foundation for logic and function theory, not as a direct attack on Hilbert. Still, it had the effect of answering Hilbert's decision problem in the negative. Kurt Gödel's presence was somewhat spectral, but his remarks were incisive. I must say, he began softly, when I published my incompleteness theorems, it was not to overturn Hilbert. But I discovered that no consistent axiomatic system, if it's sufficiently strong to encode arithmetic, can be complete. There will always be undecidable statements. That effectively put an end to the idea of a single system that proves all truths. I couldn't help but express my admiration. Your work was a revelation, Doctor. Gödel. It paved the way for all that followed. Without incompleteness, perhaps we would still be trying to perfect Hilbert's program. He gave a small, almost embarrassed smile. You're too kind, Mr. Turing. But your own model of computation was crucial. It's a delight to see how your Turing machines align so well with Church's lambda calculus and with my own notion of recursive functions. It suggests there's a fundamental unity to the concept of mechanical procedure. John looked like a man surveying a treasure trove. And that fundamental unity, ironically, is that you can't solve everything with it. You can't settle all statements, can't outrun incompleteness, but you can do a great deal. So the question is, where do we go from here? The conversation flowed into the future of computing, a topic dear to my heart. I explained that if we could build a universal Turing machine in hardware using electronics, we might harness it to solve many practical problems. I imagine a machine that can be reprogrammed by altering the tape's contents so it could handle mathematics, cryptography, anything that can be coded algorithmically. It might change how we approach problem-solving in general. John practically glowed with excitement. Indeed, I've been mulling over stored program concepts, or at least the notion that instructions and data can be stored in the same memory. It's all implicit in your universal machine, Alan. We just need to put it into practice. Kurt, though, steered the discussion into deeper waters. And yet, no matter how powerful such a machine becomes, it will be subject to the same logical limitations. It cannot step outside of its own system to prove all truths. Alonzo chimed in. True, though perhaps in practical terms, such limitations might not hinder many everyday applications. The real question is whether the human mind does something fundamentally non-mechanical when it intuits new axioms or leaps to new theorems. I stayed quiet for a moment, considering. I had begun to suspect that intelligence could, in principle, be replicated by machinery. Yet I also recognized Gödel's perspective. There's a sense in which a mind might not be pinned down by any single formal system. Could a sufficiently advanced computer replicate that capacity? I wanted to say yes, but I was far from certain. My own beliefs were evolving. Eventually, we agreed that the philosophical question of whether the mind exceeds mechanical computation remains open. But in any case, Hilbert's dream of a universal, foolproof algorithm for mathematics was over. We have new dreams now, John joked. We'll dream of building thinking machines and watch as they run into Gödel's barrier themselves. We all laughed, somewhat nervously, I think. The atmosphere in that library was at once intellectually charged and tinged with the awareness that we had, in some sense, changed the destiny of mathematics. Evening wanderings and conversations. After the library meeting, I slipped out to the garden for some fresh air. The night was cool, and I could see faint stars overhead, though the house lights obscured most. I breathed in the scent of cut grass, feeling the hush outside as a respite from the lively chatter indoors. While I was out there, a bright graduate student, his name was Paul, I think, approached me tentatively. "Dr. Turing," he began, "I read your paper on computable numbers. It's quite something. But I still don't fully grasp why an ordinary mathematician with pen and paper can't do more than your machine. After all, mathematicians can be creative, can they not?" I gave it some thought. Well, the machine's rules replicate exactly what a human can do, provided the human acts entirely systematically and follows a definite method. If there is an aspect of human cognition that's beyond systematic methods, then indeed the machine won't capture that. But so far, any process we can describe clearly, we can translate into a Turing machine description. Paul frowned. "So how about insights? Sometimes we have leaps of insight. Are those algorithmic?" I shrugged. Possibly they can be decomposed into smaller steps, though we don't see them that way subjectively. It may be that at some level, all those leaps can be broken down into mechanical steps we simply can't articulate easily. Or, perhaps, there's something else going on. The question remains open, but my guess is that any process is ultimately mechanical if we had a large enough perspective. Paul thanked me, though he seemed only partially satisfied. It occurred to me that the tension between mechanical computation and creative thought would continue to occupy philosophers and scientists for decades, if not centuries. Returning inside, I found Church in conversation with a small circle of younger logicians. They were discussing aspects of the lambda calculus I was less intimately familiar with, though I recognized some of it from his classes. I lingered long enough to glean how excited these students were about the new science of computability. They recognized, I think, that we were forging an entirely new field, one that might overshadow the older formal logic traditions. A brief encounter with Gödel. Later in the evening, I bumped into Kurt Gödel again near the buffet table. He was picking at some small pastry. I mustered the courage to engage him. Gödel always struck me as a man of luminous intellect, yet personally reticent. "Kurt," I said gently, "I was wondering something. Your theorems show that for any formal system that's consistent, there are true statements the system can't prove. Does that leave room for a new kind of logic that overcomes that gap?" He chewed thoughtfully, then replied in his soft voice. "In principle, you can always add an axiom that captures one of those unprovable truths, thus extending the system. But the extended system will have its own new unprovable truths, so we never arrive at a final system that is complete." I nodded. That's what I suspected. So there's no final vantage point from which everything is decidable. "Not if we stay within the realm of formal systems and usual logic," he said. "Unless we count an infinite hierarchy of axioms or some non-effective procedure for generating them. But that's not what Hilbert had in mind." I sighed. It's a pity. For all Hilbert's brilliance, the dream just wasn't to be. And yet, look at what blossomed from that failure. We now have an entire framework for understanding computation, logic, and complexity. Gödel looked thoughtful. "Yes, it's a paradox, how a negative result can be so generative. But that often happens in mathematics. The recognition of limits spurs exploration in directions previously unseen." I saw von Neumann in the distance, entertaining a small group with some anecdote. He was quite the raconteur. Alonzo was off to the side, now apparently lighting his pipe. I felt a sudden wave of gratitude that I found myself in the presence of such brilliant minds. To me, it felt like we were on the cusp of a new epoch, one that might give rise to mechanical intelligence, or at least mechanical aids to intelligence, if the engineering could catch up to the theory. A philosophical aside, machines and mind. Much later, near the end of the party, I found a quiet moment in a corner of the main hall. The guests had thinned somewhat, and the energy was subdued. A gentle hum of conversation persisted, but the earlier bustle had died down. I took the opportunity to reflect on everything we had discussed. What did it really mean that there's no general solution to the decision problem? For me, it signaled that mathematics was deeper and more mysterious than we realized. There would always be new frontiers, new unsolvable questions, new expansions of logic. Perhaps that was a better outcome than a tidy, closed system. If it were all solvable by an algorithm, mathematics might lose some of its wonder. But I also couldn't shake the feeling that the universal machine concept hinted at the possibility of building mechanical brains. If a machine can, in principle, simulate any finite process, and if the mind is a finite process, albeit unbelievably complex, then it stands to reason that we might one day see mechanical minds. I tried to imagine what they might be like. Would they be locked into a single perspective, or could they reconfigure themselves, adding axioms at will? Could they replicate, or even surpass human creativity? I suspected that such speculation was far too early to answer definitively. But the seed was there, and the impetus from our theoretical results might grow into something no one had expected. Even as we proved a negative, no mechanical solver for all mathematics, we unlocked the door for machines to do a great deal that is effectively solvable. Saying goodbye. Near midnight, John appeared at my elbow. "Alan, I hope you've had a good evening." I smiled. "Yes, quite good, actually. I learned a lot from talking with Kurt and Alonzo, and from seeing your perspective as well." He clapped me on the back. "I'm delighted. And I do hope you'll keep me in the loop about your progress on building, or at least conceiving, an actual universal computer. I may have some lines of funding if you ever need it. The Institute has resources, and the government might be interested in large-scale computations." I nodded, though I wasn't certain how soon such a project could materialize. "I'll certainly let you know, John. Thank you for the invitation." We shook hands. Alonzo passed by with a polite nod. Gödel was nowhere to be seen. Perhaps he had already slipped away. I gathered my coat and stepped out into the cool Princeton night. I walked back to my lodging, replaying the evening's conversations in my mind. Each step felt momentous, as though I was bridging the old era of Hilbert's illusions and the new era of partial mechanization. I thought about the enchanting possibility that within my lifetime we might build an actual universal computing machine. Could it be done? How large would it have to be? Could it do more than arithmetic, like parse language or reason about chess positions? And behind all this lurked the ghost of David Hilbert, a giant whose vision of a mechanized, complete mathematics lay in ruins. Yet that same vision had led us to define precisely what mechanized meant, and thus had led us to create a new domain of knowledge. The door to a universal solver was closed, but in the process we had built a universal problem solver of a different kind, one with limitations, but also enormous potential. I arrived at my small Princeton room, took off my coat, and lay on the bed, staring at the ceiling. Eventually, I drifted to sleep, my dreams filled with images of infinite tapes, mechanical arms writing symbols, and a faint echo of John von Neumann's booming laughter. It was a night unlike any other, an intersection of minds that I suspect will resonate through the decades. Little did we know just how much it would shape the world to come: the birth of computers, the forging of AI, the transformation of society. But there, at that moment, all we knew was that Hilbert's quest had ended in a partial tragedy, and from the ashes, a new era was quietly being born. Episode 4. From the first-person perspective of Kurt Gödel. I do not often attend parties, nor do I enjoy large gatherings, for I find them overstimulating. My preferred realm is the silent domain of thought, the symbolic interplay of logic, sets, and the occasional foray into philosophical meditations. But that evening, John von Neumann had personally invited me to his home, and I felt compelled to accept. He mentioned that Turing and Church would be there, and I suspected we might discuss the end of Hilbert's program in a private conversation, something dear to my heart. I arrived somewhat late, as is my custom, stepping gingerly into von Neumann's foyer. He greeted me with a warmth that, while genuine, always made me feel slightly self-conscious. John was irrepressibly social, the very opposite of me. He ushered me into the main hall full of chatter and music, and for a moment I stood there, uncertain where to go. Then I spotted Alan Turing, standing off to the side, and Alonzo Church, pipe in hand. I relaxed a little. In short order, John guided us to a more secluded room, and from there to his library, where we took our seats. The library's spell. Von Neumann's library had a comforting stillness, despite the party continuing in the other rooms. I saw rows of books, some on mathematics, some on physics, a few unexpected volumes in Hungarian, and an entire shelf dedicated to detective fiction. He had set out brandy for us, though I only took a small amount. We settled into chairs, forming a close circle. John led the discussion. We're here, effectively, to bury Hilbert's dream, or to reflect on the fact that it's already buried. Between Gödel's incompleteness, Church's and Turing's resolution of the Entscheidungsproblem, it seems there is no going back. I felt a wave of bittersweet memory. Hilbert's vision had once been so inspiring, a complete, consistent, decidable mathematics. But my results in 1931 showed that no sufficiently strong formal system can be both consistent and complete. That alone was a severe blow. Then Turing and Church had shown no single algorithm can decide all mathematical propositions. The coffin was sealed. I spoke up, though softly. When I proved the first incompleteness theorem, I was not aiming to kill Hilbert's program. Rather, I discovered by constructing a formal proposition that, essentially, states, I am not provable in this system. If the system is consistent, it can't prove the proposition, yet we see it's true. So the system is incomplete. I paused, glancing at Turing. Alan, your negative solution to the decision problem was, in many ways, a natural sequel. You gave a machine-based formalization to mechanical procedure, and with that, you showed some statements elude any general decision process. He nodded. We found the same with Church's lambda calculus and with the notion of general recursive functions. They all converge, which is quite elegant. But yes, it means there's no effective procedure to decide all statements in arithmetic. Alonzo added, it's worth noting that this identification of computability was itself a triumph. It gave us the Church-Turing thesis, which unifies all known models of computation under one umbrella. John seemed in high spirits, if one can be so while discussing the downfall of a dream. Exactly. So the question is, how do we interpret this in broader terms? Does it mean mathematics is forever beyond complete mechanization? That the mind is special? Or might we simply say that mathematics is open-ended, always generating new axioms? I found my mind drifting to philosophical ideas I had wrestled with for years. I have sometimes suggested that the human mind might step outside any given formal system by intuiting new axioms. If we see a statement is true, we can add it as an axiom, while a machine, constrained to its system, cannot do so automatically. But I also acknowledge that might just be a romantic notion. Perhaps there is a mechanical process that enumerates new axioms. The question remains unsettled. Turing gave a small smile. I think we can systematically add axioms, though it might not feel creative. We can systematically enumerate all consistent extensions, for instance. But yes, the time or resources needed might be staggering, so from a practical standpoint, it might be that a machine can't replicate the leaps of the human mind. John, sipping brandy, interjected. And yet, we might harness these formal definitions to build actual computing devices. Machines that can do vast calculations far beyond what any single mathematician can do in a lifetime. That's what intrigues me. We know the theoretical limitations, but within those limits, a universal computing machine could revolutionize mathematics and science. I felt a stir of curiosity. It's an irony. By demonstrating the limits of mechanical computation, you and Church also gave us a blueprint for such machines. I suspect future decades may see them realized physically, perhaps using electronic components. Alonzo smiled wryly. This might be one instance where a negative result is a positive impetus for engineering. By proving we cannot solve everything, we ended up discovering how to solve many things more systematically. We lingered there, the four of us, like conspirators who had engineered a grand coup d'etat in the kingdom of mathematics. Outside, the noise of the party continued, but in that library, we weighed the significance of what we had done. Return to the party. A private drift. After our library meeting, we parted ways, promising to talk again soon. The door opened into the corridor, and the lively swirl of guests replaced the hush of that private chamber. Turing slipped outside for a breather, Church returned to mingle with some logicians, and John went to entertain other visitors. I remained on the periphery, content to observe. I recognized some colleagues, men who had studied under Hilbert or admired him from afar. They had an air of acceptance now, as though they knew the dream was gone. Some eyed me with a strange mixture of respect and wariness. I had been the first to proclaim, mathematically, the existence of statements that defy proof. Others seemed not to grasp the full import, or perhaps they preferred not to. I found a quiet corner with a small sofa and let the hum of the gathering wash over me. Occasionally someone approached, asking me a question about the theorems. One young mathematician asked if the incompleteness results apply to all possible logics, or just first-order logic. I tried to explain that my original proof was for systems capable of representing basic arithmetic. If a logic is too weak to represent arithmetic, then incompleteness might not apply, but then that logic is too weak to do interesting mathematics. If it's strong enough, incompleteness rears its head again. Others asked about the philosophical ramifications. Did my work prove that there are mathematical truths that we can never know, or that we can never prove? I tried to clarify that my theorem only states they can't be proven within the system's axioms. One can add new axioms that settle the statement. The question of unknowability is more subtle. One might know the statement is true if one steps outside the system, but then one's vantage point changes. A moment of reflection. At one point, I took a glass of water and ventured briefly onto the veranda. The night sky was clear, the moon bright. I gazed upward, letting the cosmic vastness dwarf the concerns of formal logic. I mused that, in some sense, incompleteness might be a reflection of an even vaster cosmic truth. No matter how we try to capture reality in a finite system, reality might always exceed our formulations. Mathematics, in its pure form, can feel like a platonic realm, eternal truths waiting to be discovered. Yet, the incompleteness theorems imply that even that realm's structure is not fully capturable in a single finite description. It's open-ended, in flux, perpetually incomplete. One might say the same about the physical universe. Perhaps the human quest for knowledge is similarly unbounded. I breathed deeply. I am not a religious man in the traditional sense, but the infinite complexity of mathematics sometimes awakens in me a sense of awe. Hilbert's dream was a quest for finality, but we discovered that finality is unattainable. Yet from that unattainability emerges an ongoing journey, an infinite horizon of discovery. Encounter with von Neumann, near midnight. I decided to return indoors. As I made my way through the hallway, I encountered John von Neumann, who looked somewhat fatigued, yet still brimming with energy, if that contradiction is possible. He ushered me into a small side parlor, a few empty chairs, a table with remnants of food and drink. The clock on the mantel showed it was near midnight. "Gödel," he said softly. I wanted to have a final word with you before the night ends. I nodded, taking a seat. He sat across from me, leaning forward. I've been thinking about your theorems for years now. They moved me, perhaps more than you realize, away from certain illusions about formal systems. Hilbert was a giant, but the future belongs to you, Turing, Church, and the next generation who see mathematics not as a closed system, but as an evolving enterprise. I considered that. Yes, though I sometimes feel sorrow for having done so much damage to Hilbert's vision. John smiled sympathetically. I think Hilbert would have come around, eventually. He would have appreciated the new directions. He was no small mind, after all. And your results didn't destroy mathematics, they set it free. I bowed my head slightly. I suppose so. I do worry, though, about the philosophical directions. People interpret incompleteness in all sorts of ways. Some say it proves the mind is not mechanical, others that it only proves formal systems must grow. We can't settle that here. He reached for a glass, found it empty, set it back down. Perhaps not. But for me, the practical outcome is that I want to build computing machines that leverage Turing's and Church's definitions. We'll see how far we can push them. Even if they can't decide everything, they can do wonders with what they can decide. I found this ambition both admirable and slightly terrifying. Yes, machines might accelerate mathematics, science, cryptanalysis, who knows what else. So perhaps Hilbert's funeral is also the birth of a new era. I can only imagine what the world might look like if we had electronic universal machines performing millions of operations per second. Entire fields might change overnight. He nodded with fervor. That is exactly what I foresee. We might develop computations so complex they're beyond human capability to check by hand, yet we'll trust the machine because we know it follows a mechanical procedure, one we can, in principle, verify. I exhaled, feeling a sense of history swirling around us. Then let us see if that future emerges, I said quietly, and let our successors figure out how to navigate the limitations we've uncovered. The party's end. Shortly afterward, John escorted me to the door. The house was thinning of guests. A few lingered in corners, quietly discussing mathematics or sipping the last of the wine. I fetched my coat, offering a polite goodbye to John and a final nod of acknowledgement to Alonzo and Alan, who were speaking with a small group in the hallway. Stepping out onto the porch, I felt the cool air envelop me. I found a taxi waiting. John had thoughtfully arranged for rides. I climbed in, and as we drove through the dimly lit streets of Princeton, I looked out at the silent houses, the glowing street lamps, the occasional shadow of a strolling couple. My mind drifted back to the conversation in the library, to the hush of that moment when we recognized that Hilbert's dream had indeed ended. Yet my sense of sorrow was tempered by a quiet excitement. If mathematics had proven itself incomplete, if no mechanical solution existed for all statements, if the horizon of truth perpetually receded, then mathematics was, in some sense, infinite in scope. That seemed a cause for celebration more than lamentation, for it promised we would never run out of discoveries. I thought of Turing's enthusiasm for building machines, Church's unwavering logical clarity, and von Neumann's unstoppable drive toward the future. They seemed unstoppable forces, forging a path that would define the 20th century and beyond, and I, the reluctant instigator with my theorems, had set them on that path in part, though I could not have predicted the scale of the transformation they might unleash. We reached my home. I paid the driver, stepped out, and entered my quiet abode. The stillness welcomed me, and I felt the relief of solitude after the crowd. But my thoughts kept churning with echoes of the night. I poured a small glass of water, sat at my desk, and gazed at my notebooks. The pages of symbolic logic seemed strangely alive, as though full of hidden potentials. At last, I let my head rest, imagining the lines and curves of formal systems swirling, generating statements, some provable, some not. I thought of Turing's hypothetical machine printing symbols on an infinite tape, never exhausting the possibilities, never quite reaching an end. And in that I felt a silent awe at the inexhaustible nature of mathematics, and indeed of the human quest for knowledge. Thus ended that evening in my life, an evening that I would later recall as a pivotal moment. Four men in a library, quietly acknowledging the funeral of Hilbert's grand vision, and in so doing, lighting the embers of what might be the next great revolution, the age of computation, the age of partial mechanization, the age where logic meets engineering to transform the world.